Now our main task for today is to find these pure states of the square of the angular momentum operator. Now to build up to that, as I have expressed to you in the past, one of the best ways to attack a more complicated problem is to first solve a simpler related problem. And in this case, what we're going to do is, before we jump into solving the full L squared problem and finding its pure states, let's actually look at LZ, right? We'll probably learn a lot along the way, and we see that the LZ operator is quite a bit simpler than the L squared operator. So we're going to begin actually with LZ. So let's begin with pure states of the LZ operator. Now, before jumping in to solving LZ, first I'd like to convince you that we aren't missing out on anything by focusing on the LZs. And what I want to do is I want to actually check, right, whether or not pure states of LZ can also be pure with respect to L squared, right? If that's at least possible, then focusing on these LZ squared states is probably not a very bad idea to start off with. We won't be losing anything if they can also be pure with respect to L squared. In other words, what I'm asking is it possible that if I'm pure with respect to LZ, is it possible that I can have zero uncertainty in LZ, and at the same time, a pure with respect to L squared would mean I have no uncertainty with the value of L squared? Is it possible that this product could actually be equal to zero? And the way to address that question is always to actually compute the commutator between these two observables. I want to compute L squared with L hat Z. Right? Because we know from the generalized Heisenberg uncertainty principle, if this commutator isn't zero, then it will be impossible to be pure with respect to both at the same time. So I want to make sure I won't be completely wasting my time here. So let's see if it's going to be at least possible. So if I compute this commutator, we can think about what this would mean mathematically. Let's look at our operators. So LZ, well here, L squared was actually fairly complicated. LZ was fairly simple. H bar on I, d by d phi. Now, when we look at the L squared operator, I want you to notice something very special about it. Here it is, right? The question is, will this commute with LZ? Now, LZ is just a constant times d by d phi. So we can always pull the constant out. The real question is, does d by d phi commute with L squared? Well, when we look at the first piece of L squared, d by d phi certainly commutes with d by d phi squared, right? Because if I do the second derivative acting on the first derivative, that's just the third derivative. And then if I do the first derivative acting on the second derivative, that also is the third derivative. So LZ commutes at least with this second derivative piece. I also, though, have in L squared these parts. H squared is a constant. That will certainly commute. But how about d by d phi with 1 over sine squared theta? Notice, though, that d by d phi is a partial derivative. By its very definition, the partial derivative with respect to phi treats theta as though it were a constant. So this theta squared, while I'm dealing with the LZ operator, is treated as a constant. And because derivatives commute with constants, you can always pull a constant out of a derivative. We know d by d phi will also commute with the sine squared theta part. So LZ commutes with the first piece of L squared. If we now look at the second component of it, the story is very similar. One piece that I have to contend with is whether or not d by d phi commutes with d by d theta. Well, if I do the d by d phi acting on d by d theta, that's just the second mixed partial derivative. And famously, mixed partial derivatives do not care on the order in which you carry out the derivative. So d by d phi will commute with d by d theta. The remaining pieces in this second portion, again, are sine thetas, which are constants with respect to d by d phi. So those will commute. And so we conclude, therefore, that LZ will commute with both parts of this L squared operator. I've been looking at this, but this is really just the same components as the L squared operator. So therefore, L squared, which has all of these various messy pieces, it's minus h bar squared on sine squared of theta, multiplying d by d phi squared plus this sine theta, sorry, I have to scrunch it in, d by d theta, sine theta, d by d theta, right? All of those pieces, all of those commute with d by d phi. So this commutator is 0. So it is therefore possible that we could find, if we find pure states of Lz, that they could in fact also be pure states with respect to L squared. And there's something even a little more deep about this result, and that is that, well, I have here a special case of what are known as compatible observables. And compatible observables, so I just want to make an observation on these. Compatible observables are when I have two observables where their corresponding operators actually commute with each other. Now, we've seen an example of this in the past. The example that we've seen of this in the past is where, you may recall, we found that the Hamiltonian operator commuted with the parity operator. And because that was 0, that then told us that any pure state with respect to H, right, the Hamiltonian, had to be, because of this commutation relation, pure with respect to the parity operator. And that would be very nice, right? Because if Lz squared, if Lz and L squared commute, and we have this property that that implies that a pure with respect to one is a pure with respect to another, well, then we're definitely not wasting our time looking at these Lz pure states. Now, there's just a slight technical issue that arises. This implication, you might recall, deep in the bowels of the proof that we gave when we were studying parity, was the key fact that for any value, pure state value of the Hamiltonian, there's only one possible state. That's a property known as non-degeneracy. In general, right, my two operators, such as L squared and Lz, might have multiple states that have a particular pure value. We may not have that special property that allowed us to prove this particular case. There is, however, a generalization of the same proof that we gave. And that generalization says that for compatible observables, that if A commutes with B, right, then that does imply something very important about the pure states of those two observables. It implies that we can always find a complete set of pure states, right, that are pure with respect to both observables, A and B, simultaneously. In the parity case, you might recall that when we looked at not bound states, but scattering states, it turned out that, in fact, for scattering states, there can be two scattering states for a given energy, whether left incident or right incident. And in those cases, the pure states might not be guaranteed to be pure with respect to parity, but we were always able to construct from them states that were pure with respect to parity and also pure with respect to the energy. And there's a general fact that you can always perform such a construction, where if your two observables commute, there is some set of pure states out there, right, that completely describes the pure states of A and the pure states of B, and all of those states are simultaneously pure with respect to both of those observables. So I'm putting a star on this statement because this is the one statement so far, right, in the entire course where we haven't shown you from first principles why we can expect it to be true. This is the one fact we are going to ask you to take on faith. But after all, we have to leave something for your future quantum mechanics courses. Now, with that observation made, the application here is pretty simple. all that it is saying is that if I find my pure states with respect to LZ, I don't have to worry that I'm messing anything up. They will definitely allow me also to look at, I can arrange things so that those pure states that I find with respect to LZ will also be pure with respect to L squared. And it's the L squared pure states that we're really after. So we're not losing anything by focusing this discussion on finding the pure states of LZ. The gain, though, is we begin by looking at a simpler problem, something that will be easier for us to solve and which will give us experience in the more complex problem that we will be facing next.